Welcome to part 2 of case study ex4, which will describe how to apply various Java concurrency mechanisms. In particular, case study ex4 compares and contrasts the programming models and performance results of Java parallel streams, completable futures, Project Reactor, RxJava, and Java structured concurrency frameworks that are applied to download, transform, and store many images from a remote web server. Part 2 of this case study focuses on modern Java implementations that use the parallel streams and completable futures frameworks. And we compare and contrast that with what we did in part 1, where we looked at Java structured concurrency mechanisms. You can get this code from the ex4 project in my Loom directory in my live lessons GitHub repository. So once again, we're in the ex4 directory in my IntelliJ project, and we're going to take a look this time at 2 more of the implementations of our program that is intended to compare and contrast different models of concurrent programming in Java. In part 1 of this lesson, we talked about structured concurrency, and we also talked about sort of a hybrid structured concurrency model that mixed some of the structured concurrency techniques with Java sequential streams. This time, we're going to take a look at using Java parallel streams and also Java completable futures. So we'll start out our code walkthrough by taking a look at the parallel streams test implementation, which downloads, transforms, and stores image objects using the Java parallel streams framework. As you can see here, the run method uses parallel streams, which is very straightforward. We take the list of URLs and turn it into a stream. In fact, we turn it into a parallel stream. We then go ahead and use the map intermediate operation to transform each URL to an image by downloading each image using its URL. And we do this by using the download image method. You can see what download image does. It goes ahead and synchronously uses the blocking task manage block method to download the image in the fork join pool's manage blocker mechanism, which will expand the pool as necessary to deal with the blocking that takes place here. So that's a very clean and conventional way of doing things. We then go ahead and use the map method again to transform each of the images. And if we take a look at transform image, you can see it goes ahead and takes the list of images, image transforms, and converts them into a parallel stream, and then goes ahead and transforms each image. So this will again run in a parallel stream, and we get back essentially a parallel stream from this. And we're then going to use the reduce method to convert the stream of images into a simple stream of images. Notice we cannot use flat map here to do this. We can't use flat map here because flat map has that weird, bizarre semantic that it does not work for parallel programs. It only works for sequential programs, or it enforces sequential behavior. The last thing we do is we take this parallel stream and then we store all the images in parallel using the store image method here. And once again, store image takes the image. It uses the blocking task manage blocker method to use the fork join pool manage blocker mechanism to go ahead and store the image on the file system. And store image is just a kind of a wrapper class that stores the image and it writes it to disk. And so we use the manage blocker mechanism approach provided by fork join pool and my blocking task wrapper in order to make sure that the thread pool will be expanded, the common fork join pool will be expanded as needed if the call is blocked for any length of time. And when we're done, we print the statistics out. So this is a very, very straightforward way to get parallel computing. Let's now turn our attention to the completable futures test implementation. You can see here that this uses a sequential stream to guide the overall structure, but it uses completable futures to do the computations asynchronously. The first thing we do is we get a list of URLs and turn that into a sequential stream. Then for each URL in the stream, we're going to call the download image async helper method here to map this into a completable future to an image that's being downloaded. And here's how we do that. We go ahead and we take the URL and we call the supply async factor method on completable future. And we use that in conjunction with the blocking task manage block method to do this computation in a way that will expand the size of the common fork join pool, the number of threads in the common fork join pool, as threads happen to block. And as they block, we'll call download image, which may block, probably will block. And so that'll expand the number of threads in the common fork join pool. So this comes back as a completable future of images, which are turned into, of course, a stream of completable futures to these images. We then take each of those completable futures and we call the apply transforms helper method using flat map. We can use flat map here because we're not trying to make this be a parallel stream. It's a sequential stream that's doing its processing asynchronously with the completable futures framework. So we call apply transforms, and we go ahead and convert the list of transforms into a stream of transforms. And then for each transform, as the image future completes, meaning it's been downloaded, then we go ahead and asynchronously apply the transform to filter or modify the image according to the transform: grayscale, sepia, tint, and so on. If you take a look, we'll end up here with a stream of completable futures to images, and then we take each of those and we call the store an image async method, which uses then apply async and the blocking task to go ahead and store the image on the local device. And again, we use the blocking task manage block helper method in order to make sure that the fork join pool, the common fork join pool, can be expanded as needed as things block on I/O, in this case on writes. And you can see that we now go back over here to where we came from, and we end up with a stream of completable futures to files, because we've stored those images in files. And then we use the futures collector to collect those into a single completable future to a list of files. And then the last thing we do is we block until all the processing is complete. All this stuff is taking place concurrently. And if you take a look at the futures collector, the main method here that does the coolest thing is the finisher. You can see the finisher takes a list of completable futures, in this case to images, to files, and it's going to go ahead and return a completable future to a list of files. And it does this by using the arbitrary arity all-of method on completable future to essentially create a single completable future that is triggered when all the asynchronous processing is done. And in that case, we turn that into a stream of completable futures. We use join to turn them into essentially the type T, which in this case is file. And then we collect those things into a list. So that's what we get back here as the result of calling collect on this. We block, and then we print the results out. So that's the end of the completable futures implementation. If you look carefully between these two implementations, I think it's probably the case that the parallel streams version is more straightforward to understand. The completable futures version makes sense if you understand how completable futures work. And I think it's probably also, at least from my perspective, the parallel streams implementation is at least as easy to understand as the one that uses the structured concurrency models, which just required all this extra ceremony to have all these scopes that are involved here. And likewise, the hybrid structured concurrency model, I think that the parallel streams approach is arguably as easy, if not easier to understand, because it localizes all the concurrent processing in a much more convenient single pipeline-like model.